Hi everybody, welcome to our next topic in grade 12 physics. Today what we want to look at is kind of building an idea of electric and magnetic fields and how they interact with each other. And what we want to look at today is how charged particles behave in magnetic fields. And so let's consider, to start with, just we have some sort of charged particle here. Let's say it has a positive charge and it's in some sort of magnetic field, let's say a bar magnet. And so one thing we can observe, no matter where I put this charged particle, whether where the field is strong, where it's weak, where it's pointing in any direction, no matter where I put this positive charge, it never experiences a force. But if you remember an electromagnet, what it is, it's actually a moving electric charge that then causes a nearby magnetic material to experience a force. And so Newton's third law then says that there should be some sort of a force acting to counteract that, or maybe not. There should be a reaction force to that. And so clearly there's something has to be going on here. Because what we're saying is that if we have, let's say, a wire here where we have electricity flowing, which is just charges, remember, it's going to create a magnetic field around it. So we talked about this before. So we have a magnetic field, and that's going to be causing an object over here, let's say a magnet, to experience a force. Well, Newton's third law says then that this magnet to then be causing a force on this wire. But you can try this at home all you want, that no matter where you put, no matter where you put this positive charge, a magnet won't actually cause a force on it. So something strange has to be going on here. Luckily, it isn't too strange, because I intentionally kind of glazed over a missing part of the puzzle here. It's the fact that we have to have a moving charge. So it's not enough that a charge is in a magnetic field, it's that a charge has to be moving through a magnetic field, and then it will experience a force. And this is something that, again, will agree with Newton's third law from the idea of an electromagnet. So it actually, the magnitude of this force is given by this expression here, QBB sine theta. Q being the charge of the particle, of course, in coulombs. V being the speed of the particle in meters per second. B is going to be our magnetic field. So this was probably introduced to you in grade 11. Again, I'm sure there's a really good reason why it was B. I don't know what it is off the top of my head, but I'm sure there's a really good reason. And we're going to be using the unit Teslas. And that's spelled wrong, so let me fix that right now. It's named Tesla's after a gentleman who had a lot to do with electricity and magnetism, and actually the reason we have electricity in our homes today has a lot to do with this guy named Nikola Tesla. But anyway, so we call the magnetic field the Tesla, and what 1 Tesla is 1 kilogram per coulomb seconds. So it's a way to measure the magnetic field. So again, anyways, to find the magnitude of the magnetic force, we multiply the charge times the speed times the magnetic field. And then we're also going to multiply it by the sine of the angle between the velocity and the magnetic field. Because remember, those are both vectors. And we're going to multiply those two together. So this is how we're going to figure out how big that force is. The direction of the force is going to be given by the right-hand rule. And here's kind of a schematic picture of it. And again, you probably remember a bunch of your right-hand rules from grade 11. And this one is just kind of an extension of, I think it was probably right-hand rule number 3 you guys talked about. Kind of like the motor principle from grade 11. So your thumb represents the direction of, actually, let's get rid of that I there. This is going to be the speed, or sorry, the velocity, which way the particle is moving. B is going to the direction of the magnetic field. And remember, the magnetic field, by definition, B points in the direction, let me write that down somewhere. Let's go here. So B, by definition, points in the direction that a north pole would experience the force. Just like that for an electric field, the field lines point the direction that a positive charge would feel a force. The B field points the direction that a north pole would feel a force. And then FM, which is the palm of your hand, you can imagine pushing it. That would be the direction that this particle would experience a force. And so there kind of is our explanation of what sort of forces is going on for a charged particle moving through a magnetic field. So before we get too far, I want to spend a little bit of time examining this sine theta business right here. And so what I've got again right here, this is just the graph of sine theta, so hopefully you guys have seen this sort of graph before from earlier math classes. But notice two important things here, that it's at a maximum of 1 when the angle is at 90 degrees, and it's at a minimum at 0 or 180 degrees. So what that means for us is that the magnetic field is a maximum when the particle moves perpendicular to the magnetic field, so that means that the particle is moving this way and the magnetic field is this way, or that the magnetic field is, or sorry, the magnetic force is a minimum when the particle is moving parallel, or I guess anti-parallel to the magnetic field. So any sort of case like this, there will be no force between it. So in order to have a force on a charged particle, you need to have the particle moving across the magnetic field. So again, I'm not sure how far you guys are in calculus and vectors, but if I go back to this other page here for a second, you might also see this. So I'll write it like this. And if you don't have calc and vectors, you haven't got there yet, don't freak out. But it really should be written like this, as a cross product. So I'm not sure again if you're at the cross product or not yet, but if you get there or when you are there, that's actually how it's written. It's the magnitude of this, sorry, a force is given by the cross product of V cross B times the charge. But anyways, so we want to have this particle moving across the magnetic field in order to experience the force. And notice that if the charge is negative, if Q is negative, all that means is the force comes out as negative, and what that's going to represent is that the direction will be the opposite from what we thought. So our right-hand rule is going to tell us that the direction, let's say, is this way. So this is if our Q is positive, but if our Q is negative, like an electron or something, all that means is we have to reverse our direction. That's it. So the magnitude will be the same, so the FM will still return the right magnitude. Our direction will just be opposite from what we expected. So here's kind of our idea, and notice again that the direction for this this force is perpendicular to the direction of the speed, or so I guess velocity, and the magnetic field. So what that means is we get some pretty cool motions coming out of this. The magnetic force is always perpendicular to the motion of the particle. So what that means is this force cannot make a particle ever get faster or slower. All it can do is change the direction. So what that means is it can never ever do any work on the particle. So the magnetic force cannot do work on this particle, a charged particle, so that it cannot add energy to the particle. So what this means is that actually can only make the particle curve. And what's really cool is that if the magnetic field is actually strong enough, like it is in this case here, this particle will actually move around in a circle. And this is pretty neat. So let's kind of examine this diagram right here. So let's start with maybe picking off a point, let's say right here. So let's pretend the particle is right there. So the red line represents the direction of motion of the particle. So again, if we're going to use the right-hand rule, that would be the direction of my thumb. So my thumb would point along that direction. The B field here is pointing down, so my fingers on my right hand should be pointing down. And if you've done that properly, you should be noticing that your palm is pointing in the direction of the black arrow, the FM. And that's going to be pointing toward the center of that circle. And if you continue spinning your hand around, your palm of your hand will always be pointing towards the center of that circle. And again, what's really neat about that is that's very similar to that circular motion idea we've been talking about a lot. So we did like gravitation or uniform circular motion in our, I think it was our first unit we did this in. So there's lots of cool spots we can see this cropping up. So this is a really neat idea that we can actually get circles out of magnetic fields. And so right up here, this website, we'll spend some time in class poking around at some of the cool little applications on this website here. But if you have some free time tonight and you want to take a look at that, I encourage you to play around with some of the simulations there. And again, we'll explain them more, but if you have some time, poke around on there. You can see some of the circular motion, change some of the factors like the B field or the speed or the charge, and see what sort of effects you're going to have and see some of the cool shapes you can get. We'll, again, talk more about that in class next. All right. So before we get too far, time for a quick check. I want to test what you guys have picked up so far. So here's an example. I have a particle moving in. The particle is this yellow ball here. It's moving with this speed v in this direction. And I want to know what's going to happen to this particle. And the magnetic field is indicated by these. So I hope you remember again from grade 11 how to know how to draw three-dimensional sort of vectors in a two-dimensional page or computer screen, and we're going to be using this analogy of a dart. So if you imagine what you would see if a dart was thrown away from you, you'd be seeing the tail feathers of a dart, so you're seeing an X. And if you have a dart thrown towards you, you'd be seeing a point. And so right now we're seeing an X here, so this means the B field is heading away from us. So the B field is headed towards, or into the page or into your computer screen. So what I want you to do is, let's imagine to begin with that this charge is positive. It's heading this direction, and the B field, of course, is pointing into the page. And I want you to pause the video for a second and think about what direction would this particle move. So think about it for a second, pause the video, and when you're ready, start it again. All right, so hopefully you got an answer, and you're ready to make your prediction. So what do you think? B field into the page, particle moving to the right. What direction will this move? Well, I'm getting, if I use my right hand rule, make sure you're using your right hand, not your left hand, that the particle is going to move sort of in this direction. Should be a loop kind of going like this. Again, I can't really say for sure how tight that curve will be. Maybe it'll be more of a gentle curve, right? But it should be curving to the particle sort of, let's maybe try that one again. Curving to the particle sort of left, because it's right-hand rule like that. Because the right-hand rule, again, finger should be into the board, thumb should be pointing along, and the palm will be pushing to the left of that particle's motion. All right, so there's the positive. So again, same sort of thing. Let's repeat the process, but using the negative particle. So again, pause the video, think about what you'd see for a negative, and I'll invite you to restart it when you think you've got an idea. All right, so hopefully you got an idea. So what do you think is going to happen for this case? So what we're going to see again, B field is the same way. The right-hand rule is going to be the exact same thing. But now since we have a negative particle, what that means is our force will actually be the opposite direction of what the right-hand rule predicts. And so we'll be seeing sort of this motion. So we'll be seeing the curve going in the opposite direction. And one more question before we leave this little quick check. Out of the options, I'll call them A and B. Assuming all other conditions were the same, like mass and speed and all that sort of stuff, which particle would have a bigger charge, do you think, here? A or B? And actually, I think that's going to be my first question for the little quiz here that I put up there. So which charge, again, has the larger mass, or larger charge? So it's QB and QA. How do they compare? Are they greater than, equal to, less than? What's going on there? And again, assuming they have the same mass, the same speed, I guess it's MA equals MB, VA equals VB. All that other sort of stuff is the same. The only thing that's different is the charge. Which one's bigger? And that's the question that'll be on the quiz. So think about that for a second, so you can answer that. And let's move on to some applications. So I don't want to spend a whole lot of time on these, but I want to talk about some pretty cool applications of this motion you're going to get from charged particles in magnetic fields. So one of the biggest things you're going to see are particle accelerators, and you'll be doing a little bit of work on these for me later on. So I don't want to spend too much time on this right now, but pretty much you have these particles that are moving around in circles, and the magnetic field is what keeps them going around in circles, because you know from Newton's laws that objects without a force would move in a straight line, and so the magnetic fields would actually keep pushing them around. So you have these objects which are enlarged here, and so we have objects that are pushing them kind of along in a curve, so each time they're being shoved or turned to be moved around there. And at the same time, there's electric fields that are causing these things to accelerate and move along to speed up. So the magnetic field keeps them going around in a circle, and the electric field would actually be speeding them up. So again, I promise that we'll do a little more of that, but you guys are doing some work on that on your own, so I'm going to kind of leave that a little bit vague for now. But something else that's kind of neat, and we'll be doing a little bit of playing along with cathode rays in class. But here's like a kind of a schematic of a cathode ray tube and an experiment you can do to kind of get what's called the charge to mass ratio. So one of the ideas here to get an idea of how big electrons are. So again, if you know the charge of an electron or you know the mass of an electron, you often want to find, well, what is the other one? And one of the quantities you can get, if you can't, let's say you know the charge, because again, Millikan can find the charge of an electron for us. And you want to know the mass. but weighing the mass of one electron is pretty hard. But if you get the ratio of charge to mass, you could actually get it. And so this is what an experiment that was done to do that. And the way it was done was there was these two plates here, and you put an electric field across it. And so if you put an electric field across these two plates, you know that's going to cause these cathodes. And hopefully remember I mentioned briefly in class that a cathode is actually just a bunch of electrons. So all these electrons are coming out. And if you have electrons in an electric field, what's going to happen? Well, they'll be accelerated. And so you have these electrons naturally kind of take this path here. But at the same time, you're going to have these coils. I'll do them in red here. These coils that have electricity running through them, and coils that have electricity through them produce magnetic fields. And if you have a charged particle moving through a magnetic field, well, that's going to cause electrons to tend to go this way. And you can actually play with changing the magnetic field from the coils and the electric field from the plates, kind of canceling each other out to get the electrons to go straight through. And by measuring the ratio of those two forces, you can actually end up, and again, your textbook, if you're interested, goes through the derivation here, but a very nice expression for the charge to mass ratio. It only depends on the electric field, which again is pretty easy to calculate if you know a little bit about the parallel plates, and the magnetic field generated by the currents, which again, you can calculate with a little bit of physics. So there is a pretty simple, quick way to calculate the charge to mass ratio of the electron. All right, two more quick applications here. A mass spectrometer, so a way to actually know a lot about elements. So chemistry uses this property, or this kind of technique quite a bit. So you have this sort of ion or atom or molecule, you don't know exactly what it is. So what you do is you ionize it, you put a charge on it, you run it through a magnetic field, and the magnetic field will cause it to curve, but the amount it's going to curve will depend on its mass. And so by measuring exactly where it comes out of this magnetic field, you can get a measurement of its mass. So by knowing its mass, of course, in chemistry, you can do all sorts of crazy stuff with it. So you could talk to one of your chemistry teachers, and I'm sure they can do all the lovely stuff you can do with knowing the mass of a molecule. Yeah. Demonstrate like mass spectrometry. Okay. And the next thing that I think is really cool, it's on actually the cover of your physics textbook, this thing called the bubble chamber. And this is something that, it's a way to detect something called elementary particles. So when you're looking at the most basic fundamental properties or pieces of matter, it's kind of difficult to get actually holding chunks of these things and measuring them and weighing them and doing that sort of stuff. So indirect evidence is one of the easiest ways to do it. So one of the things you can do is look at what sort of path do these particles follow. So for instance, maybe over here we've got some sort of source that's making these particles, and they come flying off at incredibly high speeds. And if you notice, let's see if I can find a good one here. Well, here's, all right, let's see right here. So if you kind of look around here, you've got, it looks like coming out of nowhere. Try that again. A little curly kind of thing, just appearing out of nowhere. We've actually got, it looks to me like you've got probably a particle coming in from here with not leaving a trail, and then right here, it splits into two different pieces. And one piece curls to the right, and one piece curls to the left. So you've got a curl sort of going this way, and you've got a curl going this way. And they're different sizes, and they're different radii, and they're different lengths. So first of all, why would they be hurling in different directions? Well, it's because they're different sign charges. One would be positive, one would be negative. And if you knew the sign of the magnetic field, you could actually tell the sign of the charge of this thing. And furthermore, if you knew the strength of the magnetic field, and you knew how wide or the radius of that curve, you could actually get a measurement of the charge to mass ratio then of that particle. So by looking at what these particles do, like let's say this one's got a really nice spiral here, you can actually get a measurement of what these particles are kind of like, the properties of them, but actually measured. Like when I say measure, we put them on a scale. So you can get a lot of cool indirect evidence just from this pretty cool idea that magnetic fields make charged particles curve. All right, so I just wanted to introduce again those sort of 4 applications of this pretty cool physical phenomena. So let's just do one quick number crunching kind of calculation here. And we have an electron. We're going to launch it into a uniform magnetic field with some velocity, and I want to describe its general motion, and I wanted to describe the radius of what I've called its orbit. So again, I'll have you pause the video here for a second, think about these questions, try them on your own, and then restart it when you think you're ready. All right, so hopefully we've got an idea now. So let's kind of sketch this setup here. So we have an electron traveling to the right. So I'll do my electron in blue. And it's going to be hitting a uniform magnetic field going up. Oops. Let's see, magnetic field, let's make that then, let's make it red. And I want to know, what is this thing going to do? So we'll use our right hand rule. So our fingers are going to point up. My right hand thumb should point to my right to match the direction of the electron flow. So my palm right now should be pointing towards me, facing me. But because we have an electron which has a negative charge, I know that I actually have to reverse the direction. So my electron right here is going to be traveling then into the page. So it's going to start curving into the page. Maybe I should have drawn this another way. Yeah, let's change this just slightly here. So instead of saying that the B field is up, let's change that just slightly so I can speed here to draw. So let's have the magnetic field then uniform magnetic field going into the page. Let's redo that right-hand rule then. So again, my fingers now should be pointing into my page. My thumb would be pointing to the right. So my palm right now would be pointing up the page. But because it's an electron, it has a negative charge, we should reverse its role. So the electron's motion would actually then be pointing sort of down, so it should be going kind of in this way. Assuming my magnetic field is completely uniform, it should eventually go around in this sort of direction. Like this. And unless I change something like the magnetic field, it's going to keep going around in this direction, around and around and around, forever. All right, and for the next part, I want to know the radius of its quote-unquote orbits. So I want to know what is this distance from here to here. All right. So we need to figure out how the heck we're going to do this. Well, we know this thing is traveling in a circle, as poorly as that circle I've drawn is. And we want to know then what sort of things are going on. So if we want to travel in a circle, we know that the force has to be given by this expression here, just because that's our expression for uniform circular motion. This thing's going to be traveling uniform circular motion because the magnetic force can't speed it up or slow it down. We know that the magnitude of this force is going to be given by QVB sine theta. And let's just quickly address that sine theta business. So what is that angle between here? Well, it's the angle between the electron's motion, so this vector here, and the magnetic field, which is into the page. And you might be thinking, oh my goodness, sine theta is going to be changing all the time. But luckily it's not, because every time we have a velocity vector, it's always still perpendicular to the magnetic field. That's the nice thing about free space. We can have infinite vectors that are parallel or perpendicular to each other. So sine theta will always be 1. So we can kind of drop this and just say it's 1. And, oops, sorry about that. And we end up with QVB equals mv squared over r. And if we just keep going, we're trying to solve this guy for r. So one of my v's will cancel. So I'll have QB equals mv over r. M is then mv over qb. And the numbers we should be using again are v is our speed, which is a constant in this case. B is the magnetic field. M is the mass of an electron, and Q is a charge of an electron. So I'll leave that to plug it in for you, but I'm getting a pretty small number here. I'm getting a radius of 1.39 by 10 to the minus 5 meters. Or to put that somewhere else, I'm getting, what is that? I guess we can say then 13.9 micrometers. So quite a small distance. But anyways, that's it's pretty reasonable for an electron traveling pretty fast. It's going to be traveling around in a fairly tight circle. So there is our our answer there. All right, so again, that's pretty much it out of me. So again, I just want to point out that the overall kind of big takeaway from today is just that, well, this is our magnetic force here. The other kind of things I talked about is the kind of cool applications of it. So I hope that makes sense, and tomorrow in class we'll play around again with those simulations on that webpage, but if you have some time, please do take a look at that, and I'll see everybody in class tomorrow. Have a good night, guys.